So hello everyone. I'm going to talk about DAS mainly. Um, just a short introduction for those who have heard about DAS and have no idea how it works. We know that DAS stands for Distributed Acoustic Sensing, and the main thing that we are made aware of in the beginning is that we are trying to measure longitudinal strain along the fiber. And we know that we are using laser pulses and some magic to do something. So, in a nutshell, fiber optics is now the commonest way to transmit information from one side of the world to the other because it's very cheap and it suffers less problems than copper cables and higher bandwidth. However, because the glass substrate where we transmit the laser pulses is not a perfect vacuum, so we have some interactions of light with matter, and that causes backscattering and reduces the range uh, on for the data transmission. That is one of the reasons that we have repeaters. That Giuseppe showed the way to use those repeaters as uh, limits for sensors, but we can also use the backscattering of the light to detect some perturbations on the fibers. So the main proposal behind DAS is that there are some imperfections inside the glass that we don't know exactly how they're distributed, how many there are, and what is their geometric relationship. But we know that they will create a specific pattern in the backscattering spectrum. And if we change something in the position of the fiber, that backscattering will change because the relative position of particles will change. So we can detect when the fiber is deformed. And if we use time gating, if we use single pulses, we can even see where the fiber is being affected by some field. However, because we don't know exactly how the glass imperfections are distributed, we need to average it over finite length, and usually from a few centimeters to a few meters. But even so, our signal to noise ratio is very low, so we usually also combine each channel into a group of channels that we call the gauge length, which is the effective size of our sensing element. Um, and on a first approach, we hear that we have a fat transfer function between strain and whatever number the interrogator is showing. And you see there's a small spherical cow there. That is the symbol for a crude approximation because we know no better. And we know no better because the problem itself is very complicated. So usually a seismic sensor will measure ground motion or acceleration. And if we really want to get into exotic parts, we might even consider a geomagnetic storm affecting a seismic sensor. But it's an easy model to understand. In DAS, we have not only the strain that affects the fiber, but also the size of the gauge length that we use and the direction from which the energy comes that will affect how the fiber responds to strain. But the fiber is also sensitive to temperature and pressure. And if we are talking about a seafloor fiber, the pressure will also affect the sediment around the fiber and the whole ground around the fiber is part of the sensing element. And the problem is still not solved because we cannot easily um, understand how this cross sensitivity affects our measurement. However, we also know that when we are working the ocean, um, things get very expensive and very quickly. So if you want to deploy an OBS, we have to pay for ship, we have to pay for the instrument, we have to hope that it comes back, and that always costs money. If you want ROVs, we can use them, but it's just point measurement, and we are very limited. Surface measurements are easier to do, but they are also usually limited in terms of resolution um, due to the increasing depth. And if we look at the distribution of our samples from oceanographic models, we see that they are concentrated along the coasts where it's easy to reach. But cables are everywhere in the ocean. We've seen a version of this image or two versions just to illustrate that we can get cables everywhere and they're already there. So we don't need to go there to collect data, even though we sometimes don't know exactly what DAS or interferometric DAS is measuring. And we can think about systems where we combine a seafloor cable with surface and satellite observations that will complement each other. So we can get high resolution at the surface with conventional methods, and we can also get high resolution measurements at the seafloor, where we usually get very low resolution, and we can adjust the parameters of acquisition depending on the objective that I want. If I want oceanographic variables with very long periods, I can just adjust my sampling rates and gauge length to those periods. If I want to track marine mammals, for example, I will increase the sampling rates, improve the noise to signal to noise ratio on certain channels by combining them and averaging them. And this will be used in conjunction with other instruments that will help us build a better picture of what's there. We can use, for example, for marine mammals, we can use traditional hydrophones to detect them and classify them. But if we combine it with distributed acoustic sensing, we can go one step further and even track animals as they move. And this is just one of example of things that you can do with DAS cable. And in this case, not only were these whales tracked with the DAS cable, but there were also sightings from shore that matched these whales. So we have things that complement each other and then can be verified. One thing that we can use DAS cable, for example, is for MCS imaging. So usually we do it with a streamer that's stowed behind the ship, and we use an active source or even natural sources, and we collect P waves, mostly because we cannot propagate S waves on the water. But if we have a cable, the seafloor, we can get all the P to S conversions that occur as the seismic waves travel through the different layers. So not only we will get high resolution, spatial resolution image, but we will also get the S waves that are lost with a towed streamer. If we use OBS, we can get those S wave conversions, but at a spatial sampling that is not comparable to the fiber optics. 10 to 15 kilometers between each OBS instead of tens of meters for the fiber optic cable. And we can also use a simple cable with an earthquake to generate subsurface imaging, because we have an extremely high spatial resolution. And here again, I say that S waves are recorded. In this case, I have P, S, and even T waves recorded, which were not visible on land stations in this case. We can also use leverage the high resolution that DAS is capable of to image small structures with ambient noise tomography. This is one example from Spica, one Jack Spica, where with ambient noise tomography, they could isolate one small basin. And if we use air guns or other active sources, we can also treat DAS records as OBS sections and process them in roughly the same way. We have still problems with amplitudes, but in terms of travel times, they are perfectly in sync and with better clocks than any instrument that we deploy on the ocean. We can also use DAS to complement information from single sensors. So in this case, we have a buoy that's anchored in a specific place, and it's recording wave heights and wave directions, but it's a single point in a very large basin. And we can use that process one bay to infer about sea state only from the pressure signals near the coast. And what we find is that we have a very good match between our predictions from the pressure signal to the observations on the buoy. There is only one part of the cable where there's not such a good correlation, but it was during a storm. So we had not only the influence of the local conditions, but also very windy conditions that didn't reflect on the pressure signal. And with some filtering on the data. So if you remember that long equation about all the problems that affect DAS measurements, the middle term was temperature. And it usually acts in a time scale that's separated from the strain events and pressure events. So we can then pass our data and start to infer about temperature signals. And in these images, I have two examples of how we can track temperature fronts, so places where the refractive index of the fiber will change due to temperature differences, and how they move along time in the deep basins. And in the larger figure, we can see on the right side some events that are going back and forth. And these, we believe that they are a mesoscale eddy that's being just pushed around by the tide and dissipating. And in the middle part, around 2,000 meters distance, we can see some back and forth events also, but with stronger signal. And these are internal tides that periodically go up and down the island slope of Madeira. And to finish, just a quick overview about the cable that we are exploiting in Madeira. It's the GeoLab fiber. It's exclusively for seismic research. It's 57 kilometers long. We've been collecting data for 2 years now, and we are using it to complement the capabilities of Madeira's Oceanic Observatory that has its own fleet of surface and underwater vehicles and we are comparing data from all these platforms so that we can build better ocean models. And finally, this facility is open for collaborative research. We have more data than we can work with. So please, if you want to do some experiments, share some data. We will be happy to work with you.